There are many different types of AC motors. There are synchronous motors, repulsion motors, universal motors, and induction motors. Of these, the induction motor is probably the one most commonly used because of several reasons. Its simplicity of construction, its relative low cost, and its ruggedness. For these reasons, you will see induction motors like this one that supply only a fraction of 1 horsepower. Others will vary in size according to the job they must do. So, in this lesson on AC motors, we'll concentrate our attention on the induction motor. Once you understand its operation, it's a simple matter to understand the operation of the other types. Now, to begin our examination of the induction motor, let's take a look at how it's put together, its physical construction. Oh, don't worry about your TVI guide for a while. We'll fill it out during the review after we finish the discussion. Bob?
Okay. This is a typical induction motor disassembled. Now, as we've said, it's very, very simple. We have the 2 end bells, the stator field windings, and the rotor. Now, let's take a look at these end bells. The end bells are used to house the bearings or the mounting devices that hold the rotor shaft in place. Now, notice there are no brushes or complicated brush holding devices at all. Just simply hold the bearings. And also inside the housing, or inside the end bells, we would find the housing that contains the stator field windings. Now, notice the simplicity of construction. We have the stator field windings, the iron core. Very, very rugged and very simple. Inside the stator field windings, the rotor. Let's take a look at this rotor. All right, the rotor has no commutator, no slip rings, and no wire windings. It doesn't look at all like the rotor used in DC motors, does it?
Not at all.
Now, this particular rotor design is called the squirrel cage rotor because it resembles the exercise cages used for pet squirrels. Like the squirrel cage, the rotor is very simple to construct. Simplicity of construction, which of course leads to lower cost of manufacture, and a very rugged design, makes the induction motor a very popular one. There are no wires on the rotor to burn out, no brushes to wear, no commutator to get scratched or pitted. All in all, a pretty good motor.
Of course, it's not perfect for every application. It does have certain limitations. But even so, it's used quite extensively. Now, there are several types of induction motors, but they all operate on the same basic principle. The same basic principle which can be illustrated like this.
Okay, what we have here is a cardboard disc, and on the disc we have, it's mounted on a pivot, by the way, so that we can spin it, and we have 2 permanent magnets glued to the disc. Thus, if we spin the disc, we have a rotating magnetic field. Now, the principle we want to show you here is that if we take another magnet, such as this compass needle, and put it on the pivot, in other words, so it's free to rotate, and we spin the cardboard disc, we have a rotating magnetic field. Now, you'll notice that the compass needle picks up the rotation of the rotating magnetic field, tries to align with it. Now, this is an extremely important principle. Let me show you that again. We have a rotating magnetic field. We have a compass needle. Look at it pick up the rotation of the rotating magnetic field. As it tries to align with the field, it begins to rotate. Now, this principle is the one that makes the AC motor operate.
In the induction motor, the moving or the rotating magnetic field is supplied by the stator field windings.
Right.
And the rotor follows this field movement because it becomes an electromagnet. In other words, when current is applied properly to these windings, a magnetic field is generated that rotates about the housing. Now, the field windings do not move themselves, and this rotor is not a permanent magnet. But watch what happens when the rotor is placed inside the field windings.
And the power is applied.
The rotor rotates. Now, it's not physically connected to the field windings in any way, but it does rotate. Why? Simply because the field windings are providing a rotating magnetic field that induces a voltage into the rotor that causes current to flow, and the rotor becomes an electromagnet. And once it's magnetized, it's got to follow the rotating magnetic field, just like the compass needle did.
Right.
Now, Bob, we should point out that this rotor is not the correct size for this motor.
No, it's a little smaller than the one that belongs in here.
Well, we've used a smaller rotor to emphasize the fact that there is no physical connection between the rotor and the field windings. Actually, there are two major points to discuss in order to understand how the induction motor operates. First, we must have a rotating magnetic field produced by the stator windings. And second, we must cause the rotor to become an electromagnet. So let's first determine how we can produce a rotating magnetic field.
Okay, coming up.
Now, these four coils represent the stator windings of the induction motor. Actually, they're wound to act like solenoids for this demonstration. And we made them out of a deflection yoke from an old television set. Of course, the stator windings in the induction motor are not made exactly like this, but the magnetic field produced is essentially the same. Now, this switch on the bottom will allow us to apply certain voltages with certain polarities to these coils. And on this chart, we'll show these polarities during each increment of time. Now, in the center of the coils, we've placed a permanent magnet with an arrow on it to show the direction of the magnetic field at any one time. Now, this permanent magnet is simply glued to a ball bearing so that it can rotate freely. Now, the object of this demonstration is to cause this arrow, this magnet, to rotate 360 degrees by causing the magnetic field produced by these coils to rotate 360 degrees. So that you can understand exactly why this happens, let's take a look at the way these coils are wound and how the voltages will be applied. Now, actually, there are really only two coils. We'll call them L1 and L2. Now, L1 was wound something like you see it. And then the core was cut in the middle and stretched apart. Now, it's still one coil, but now it's got a gap in the middle. L2, the other coil, was constructed in the same way. Now, L2 will supply a horizontal magnetic field, and L1 will supply a vertical magnetic field. So if we supply voltage to just L1, we'll of course cause a vertical magnetic field.
Like this.
And the field lines up like this. Now, this arrow, like the arrow on our trainer, points to the north pole of this magnetic field.
Right up here. And right here, Tom, we should point out that you can apply the left-hand rule and determine the magnetic polarity of these coils. We're not going to take the time to do it now, but it'd be a good idea if for the students to do that. They could actually prove that what we're saying is quite true.
Right, that's a good point. Another good point is if we reverse the polarity on L1,
make this a negative, in other words.
Right. We'll, of course, reverse the direction of the magnetic field produced by L1. And the rotating magnet will again line up with this magnetic field. Now, the same thing, of course, applies to L2. With voltage applied only to L2, we'll produce a horizontal magnetic field.
Like that. There we go.
And if we reverse the polarity applied to L2,
go from positive to negative again.
We'll, of course, reverse the direction of the magnetic field.
Right.
Now, from this, you should see that we can already produce four magnetic field directions, up, down, left, and right, simply by supplying the proper polarity of voltage to each coil. Now, we can also energize both coils at the same time and produce four more directions.
Okay, we're going to pause there.
Now, by supplying both L1 and L2 with this polarity, L1 produces an up direction, L2 produces a left direction, so the two equal fields combine and move up and left at this angle. And of course, if we reverse the polarity on both coils, we would, of course, reverse the direction of the magnetic field.
We're going from positive to negative again. Like this.
Exactly opposite polarity, and we reverse the direction of the magnetic field, causing it to move down and to the right.
Right.
Well, that essentially is what we're going to do in this demonstration. Simply supply voltage with the proper polarity to cause a magnetic field to rotate 360 degrees in a clockwise direction.
Right.
Now, we could just as easily produce counterclockwise rotation by reversing the direction of the windings on L1 and L2, but we chose clockwise. All right, Bob, let's reset the demo to the time 0 position.
All set.
Now, at this position, the pointer indicates 0 degrees. It's pointing straight up. From this, we know that only L1 has voltage applied to it. The graph shows that the value of this voltage is a positive 10 volts. At this time, of course, L2 has no voltage applied. All right, switch it to time 1.
There we go.
Now, at time 1, the pointer is indicating 45 degrees. Now, this tells us that both coils must now have voltage applied to them. Now, the voltage on L1 has dropped to 7.07 volts. And the voltage on L2 now has risen to 7.07 volts. All right, switch it to time 2. At time 2, the pointer shows that only L2 now has voltage applied. It's at maximum positive, 10 volts. L1 is now at 0 volts. At time 3, the pointer again indicates that both coils are energized. The graph shows L2 at positive 7.07 volts and L1 now at negative 7.07 volts. Now notice that the polarity on L1 has been reversed. This was done to reverse the direction of the magnetic field produced by L1. It's now down instead of up. Now I think time 4 will prove this, Bob.
Sure will.
Now only L1 has voltage applied, and of course it's negative 10 volts. Now see the difference between time 4 and time 0. At time 0, L1 was at max positive. The pointer showed that the magnetic field was moving up. However, at time 4, L1 is at max negative. The polarity is reversed, and the pointer shows that the magnetic field is also reversed. Okay, Bob, switch it to time 5. Now, once again, the pointer shows that both coils are energized. Now, notice that we also have reversed the polarity of voltage applied to L2. Now, both coils are at a negative 7.07 volts. At time 6, and only L2 has max negative applied. Now, L2's field has reversed as indicated by the pointer. L1 at this time has 0 volts applied. Now, at time 7, both coils energized. L2 at negative 7.07, L1 at positive 7.07. And at time 8, we're back at 0 degrees, where we started. And our voltages and polarities are also at the same values we started with. L2 is at 0 volts, L1 is at max positive. So we have rotated the magnetic field 360 degrees. But we used DC voltages to do it. And this is supposed to be an AC motor. Well, look at the graph of the DC voltages that we used to produce 1 revolution of the magnetic field. Here are the voltages applied to L1. And here, the voltages applied to L2. Look familiar?
They sure do.
If we connect all the voltages applied to L1 and all the voltages applied to L2, we find that we have 2 AC voltages that are 90 degrees out of phase. Well, that's why we use 10 volts and 7.07 volts. Now, 10 volts is the peak voltage of these AC sine waves. When we divide the sine waves into 45-degree segments of time, we see that these points are exactly 7.07 volts. So using these values, we constructed a sine wave that moved through 360 degrees. And then by applying these values to the trainer, we move the indicating arrow through 360 degrees. The important point for you to remember is that 2 out-of-phase AC voltages will cause the magnetic field to rotate just like the DC voltages. Only with AC applied to the coils, the rotation will be a lot smoother, and we won't need a mechanical switch. The voltage values and polarities will change automatically as the input AC changes. Now, another point is 1 cycle of AC produces 1 revolution of the magnetic field in the example that we just used. Now, the actual speed of the magnetic field of an actual induction motor would, of course, depend on the design of the field windings, the number of pole pieces, and, of course, the frequency of the applied AC. Now these field windings have AC applied to them.
Not yet.
Huh?
Now they do.
Oh, you turn the power on.
Right. We've applied
Okay,
it.
I'll start over.
Okay.
These field windings have AC applied to them in the proper phase relationship. They are producing a rotating magnetic field,
Right.
which is easily proved when this
Well,
chunk of iron is dropped into the field.
proved, Tom, not really easily, because the magnetic field is attracting the rotor toward the
You're
stator.
saying it's
Now
kind of
we've got
hard to
it.
get in?
Yeah, we've got it in there now, and if I let go of it,
It rotates.
right.
And obviously something must be causing it to rotate.
Mhm.
And that's something, the rotating magnetic field.
Right.
A rotating magnetic field. But how does this cause the rotor to become an electromagnet?
Well, you remember the requirements for induction?
I sure do. A magnetic field, conductor, and relative motion.
All right. We've got a magnetic field here that's rotating about the field windings. I'm going to take the rotor out of there and prove that we have induction taking place. Now,
Why don't you explain?
all
what
right,
you've
I'm
got
going to
there,
do
Bob?
that. This is a coil of wire. The ends of the wire are connected to a resistor that is connected to the leads on our PSM6. And the object is, if we get current to flow in this loop, we'll have current flowing through this resistor, we'll get a voltage drop, and we'll read the voltage on the PSM6, okay?
Okay.
All right, now I'm going to take the loop of wire and place it in the field windings. Now I want you to watch the meter on the PSM6 here. Now, let me apply the juice first. You may hear a little hum being picked up by the microphone because of this magnetic field. Now, as I place this loop of wire into the field windings, like this, you'll
You've
see,
got something there. There
see
it
the
is.
PSM6 indicating a voltage value.
That's induced voltage, huh?
That's right. That's the induced voltage from this loop. And you can see that I take the loop out, it goes away, put the loop back in. I've got to get the loop all the way down in there. There you go. Now we have the rotating magnetic field inducing a voltage into the loop, which we're reading on the PSM6. Now the important thing to realize here is that once we get current flowing in this loop, once we get a current flow in this loop of wire, we have a magnetic field established about the loop. Now this means that we'll exhibit a north pole on one side and a south pole on the other. Or in other words, we have magnetized the loop,
Made
right?
it an electromagnet.
An electromagnet, right. Now actually, the rotor is the same thing, or almost the same thing. And a rotor is made in a very, very similar way. Instead of using windings of wire, however, we use conducting ring on this end, conducting ring on this end, and they're joined together by conducting bars, these little white lines. And the reason I say conducting, sometimes they're made of copper, sometimes aluminum. This one happens to be aluminum. Now, current, as the rotating field goes around this rotor, current is caused to flow in the rotor, which sets up a magnetic field, and the rotor develops a north and a south pole. Now, once we magnetize the rotor, it has got to follow the rotating magnetic field, as you've already seen, just like that. Okay? That's it. The rotor follows the rotating magnetic field as soon as it becomes an electromagnet. Same thing that occurred with our little demo, the permanent magnets on the card with the compass needle.
You should point out, Bob, that the rotor also has a core made of...
Right. Now the rotor is a little different than the wire loop because it has an iron core, or a material that has a low magnetic reluctance. Now this, of course, concentrates the magnetic field and makes the rotor a stronger magnet. So the rotor turns following the rotation of the magnetic field.
But, Bob, how fast does the rotor turn?
Well, to answer that one, we've got to reconsider the requirements for induction. You remember the requirements?
I sure do. Magnetic field, a conductor, and relative motion. Now, this relative motion is between the magnetic field and the conductor. And, of course, if there's no relative motion, then there's no induction.
That's right. So we know from that then that the rotor cannot turn as fast as the magnetic field, because if they were both turning at the same speed, there would be no relative motion between them. No relative motion, no induction, no current flow in the rotor. And of course, if we didn't have current flow in the rotor, there would be no magnetic field, no magnetism in the rotor. The rotor would just be another chunk of iron. And we also know that it can't turn faster than the magnetic field, because the magnetic field is what causes the rotor to turn. That is, it's the driving force. So if the rotor can't turn faster than the magnetic field, or even at the same speed, the obvious conclusion is that the rotor must turn slower than the magnetic field, right?
Absolutely brilliant conclusion.
Good.
But tell me, Bob, how much slower?
Now, that depends on two things. The amount of internal loading and the amount of external loading. Now, what do we mean by that? Internal loading refers to the drag or the load on the motor caused by weight and friction.
You mean like it would be easier for a little guy like me to push a small light car than it would to push a big old heavy clunker like yours?
It'd be easier for anybody, Tom.
Especially me.
Right. The same thing is true of this rotor. That is, it takes a certain amount of energy to overcome its weight to cause this hunk of iron to turn. And, of course, the friction of the rotor shaft on the bearings adds to the internal load. And there's a little cooling fan built into the rotor, and that increases the internal load. Now, the external load refers to the job or the work that the rotor must do. That is, turn gears or operate pulleys, or maybe turn a fan blade.
That you just happen to have with you.
Happen to have one in my pocket, right?
Very good.
Now, when we put this fan blade on the rotor, we have increased the load or the drag on the motor. And therefore, it's going to turn a little slower. In fact, I've got to give her a little start there to get it going. Now, it turns slower.
Now, before, the rotor was turning almost as fast as the magnetic field, under a no-load condition, of course.
Right.
Now it slows down a little. Well, it slows down a lot because it's got work to do. There's more drag on it.
Right. That's the way.
So the rotor does then turn slower than the magnetic field. I think we've proved that point, Bob.
Right.
Now, the difference between magnetic field rotation speed and rotor rotation speed is called slippage. And the greater the load on the motor, the greater the slippage.
That's right. Now, since we put a load on the motor, this fan, in other words, we've caused the rotor to turn slower. Well, how do we generate enough energy to keep that rotor turning?
That's a very good question, Bob, and I hope you've got a good answer.
Oh, we do. The rotor becomes an electromagnet, right?
Right.
But how strong an electromagnet is the rotor? How strong should it be? It should be just strong enough to do the job, in this case, to keep the fan blade turning. The strength of the electromagnet is determined by the amount of current that flows through the conductors of the rotor. The more current, the stronger the magnet, and so therefore the current in the rotor is determined by induction.
I've
the
heard that
rotating
somewhere
field.
before, induction.
Mm-hmm.
Well, we know that the magnetic field strength is at some fixed level, depending on the applied voltage. And we know the number of conductors in the rotor is also fixed. So the only variable factor that could affect the amount of induction is the relative motion between the magnetic field and the rotor. Is that right?
Exactly. So if we increase the relative motion, we increase the rate or the frequency at which the conductors are cut by the flux lines of the rotating field. The greater the frequency of cutting, the more the current in the rotor, the more current in the rotor, rather, and the stronger the magnet. Now, that's why the rotor can continue to turn the fan. The load of the fan causes the rotor to slow down, just as I can do with my finger here. I can cause the rotor to turn slower. Now, as it slows down, the slippage increases. And the frequency at which the conductors of the rotor are cut by the rotating flux lines increases. More current flows. The magnet becomes stronger and compensates for the increased load. Now, there's a limit to this.
I thought there would be.
For example, if I make the load on the motor too great, as I'm doing here with my fingers, it stops. But the magnetic field is still zipping around there, right?
Right, nothing slowed it down.
No. So the frequency of cutting has gone way up. Now, from this, you might think that the current in the rotor, when I've got it stopped like this, has also gone way up. But that's not so.
Look at this. As the frequency of cutting, which is F in this formula, as the frequency of cutting goes up, X sub L, the inductive reactance of the rotor, also goes up or increases. Now we know if the reactance of the rotor increases, then of course the current in the rotor is going to have to decrease.
Right. So at this high frequency of cutting, that is when I've got it stopped, I'm holding it stopped, the reactance of the rotor becomes large enough to limit the amount of current flowing in the rotor's conductors. So too great a load will stop the rotor by increasing its reactance to a point where the current decreases. And of course, as the current decreases, the strength of the electromagnetic field decreases, the motor can no longer do its job, and it stops. Now actually, trying to operate a motor with too great a load on it will result in damage to the motor. And of course, that's why motors are rated for different loads.
That's very logical.
Okay?
Now this curve, which is known as a torque curve, will give you some idea of the relationship between rotor rotation speed, magnetic field rotation speed, and the turning force or torque generated by the motor. Now with no load on the motor, the speed of the rotor is almost equal to the speed of the magnetic field. There's not all that much holding it back. But as the load is increased, as when Bob put the fan blade on, the rotor begins to slow down. The rate of cutting increases and torque increases, compensating for the added load. But at this point now, torque is maximum. Now, if the load is increased any more, as when Bob held it with his fingers, the rotor, of course, must slow down. The frequency of cutting goes way up to the point where the inductive reactance becomes large enough now to start limiting the current flow in the rotor. The strength of the electromagnet decreases, torque decreases. The motor stops and begins to overheat. Now, if left in this condition, of course, the motor will be damaged. Now, the point on this curve where the motor is designed to operate is just about, just about here.
Right.
Now, this allows the load to change slightly without upsetting the stability of the motor.
Right. Okay, so the rotating magnetic field then induces a voltage into the conductors of the rotor, causing it to become an electromagnet. It exhibits a north and a south pole. The rotor turns at some speed determined by the load, both internal and external load. Now the difference in speed between the rotor and the magnetic field is called slippage. All right? That is the AC induction motor.
Very good, Bob. Now to summarize, let's complete the TVI guide.
Okay, I'll take item 1, which
Okay.
asks you to identify the major parts of the induction motor. A, the end bells. Remember, they just hold the bearings for the motor. B is the housing and the stator windings. Very simple and very rugged. And C, of course, is the rotor.
Right now.
There are no slip rings or wire windings. And of course, overall construction is very simple, very rugged. Okay, item 2.
Very good. I'll take this one. The basic principle of operation of the AC induction motor is conductors placed in a rotating magnetic field will become magnetized, and if allowed to rotate, will follow the moving magnetic field, as the rotor is doing in this case.
Right.
All right, take number 3, Bob.
Okay. A rotating magnetic field is achieved by applying out-of-phase voltages to the stator or the field windings, which we represented on this demonstrator.
Now, you should point out, Bob, that the most effective phase difference to use is 90 degrees, as we did.
Right. It'll work at other phase differences. In fact, any phase difference other than 0 or 180 will give you a rotating magnetic field. But as you said, the most effective, the most efficient one is 90 degrees phase difference, and that's the one that's probably most commonly used.
Right, now I'll take item 4.
All right, help so.
All right, item 4, the rotor acts like a magnet. Well, it actually becomes an electromagnet
Right.
and follows the rotating magnetic field because of induction.
Okay, and we proved that with this little loop of wire, the resistor and the PSM6. We put the loop in the field windings, and the PSM6 showed us that we did have a voltage induced into the loop, causing current to flow. Once we had current to flow, we know that the loop had to become magnetized and exhibit a north and a south pole. And once we get it magnetized, it has got to follow the rotating magnetic field.
Which brings us to item 5, which I believe you can have.
Exactly. All right, the rotor of the induction motor does not rotate as fast as the magnetic field because of several forces that act on the rotor. One, the internal load, that is rotor weight, the little fan, the bearing friction, and so on, and the external load on the motor, such as the gears, pulleys, or the fan blade, or in this case, my finger. As I squeeze it a little bit, you can see that it turns
Whatever works
slow.
the motor
Right.
must do.
So the rotor's got to go slower than the rotating magnetic field in order to have relative motion so that it can become an electromagnet.
Which brings us to item number 6 in the TVI guide, and my turn. Slippage is defined as the difference between the speed of rotation of the magnetic field and rotor rotation speed.
Right. Okay. And
All right,
remember,
item
this slippage
7.
is an extremely important one, Tommy, because without a difference in speed between the rotor and the rotating magnetic field,
Well, we won't have an electromagnet.
right, we wouldn't have relative motion, we wouldn't have induction, and the motor wouldn't work. So slippage is an extremely important aspect of the induction motor.
Now, can I get item 7?
I'll get it, all right?
All right, you can have it.
Item 7 shows you how one complete revolution of the magnetic field is accomplished by applying these out-of-phase voltages to the stator windings. Now, you can study this very, very carefully so as to fix the principle in your mind.
Which
And
was,
by the way, we might point out, Tom, and once again, that you can apply the left-hand rule to all these coils and prove precisely what we've said, right? We can develop a rotating magnetic field.
I'm certainly glad you said that, a rotating magnetic field
A rotating magnetic field.
that induces a voltage in the rotor, causing it to become an electromagnet,
Right.
which will follow the rotating magnetic field. Simple
And rugged.
and economical.
Right. The AC induction motor, because of all these facts, will be found very, very widely in your career as a technician. So study that TVI guide and learn all you can about it.
I sure
You
will.
too.